Thanks, Becky. I am now. Okay, so for the benefit of posterity, I'll just say what I've said again. I'm going to write down a proper definition in a second anyway. So we have a group G, we pick an element of G, and then we look at all x in G that commute with the given element A. So that's some subset of G, which we denote by capital C of A. So let's write down this as a definition, which isn't going to say much more than I've just said. So let G be a group. Let A be in G. So the centralizer of A is what I've just written down. So it's the following subset of G. So I'm already in the definition, I'm defining this notation as well. So, given an element A, it's interesting to know in any case which elements commute with A, and it turns out that this is a good way of generating subgroups of G. So let's prove that C of A is always a subgroup, and so that'll give us practice at using our subgroup criterion as well, which we haven't used for a little while. And then we'll do some examples of computing centralizers, and we'll observe some simple properties of centralizers. I'm not going to spend a lot of time on this. Okay, so proposition, let's just prove straight away that this is a subgroup. So let G be a group. Let A be in G. Then C of A is actually not just a subset, it's a nice subset, it's a subgroup of G. So, as almost is always the case when we're proving that something's a subgroup, we use the subgroup criterion, which we introduced quite a while ago now. So remember, there are three things to check. We've got to check that the subset is closed under the binary operation of G. We have to check that the identity element is in there, and we have to check that for each element in there, its inverse is also in there. Okay, so we use the subgroup criterion or criteria. So the first thing is closure. So we take two elements in our subset, we multiply them together and check that the product is again in the subset. So let x and y be in C of A. So we take two elements that commute with A. So let's just spell that out. So xa equals ax and ya equals ay. And we're going to consider multiplying x and y together. So that's certainly an element of G, and what I want to do is show that it's actually an element of C of A. Okay, so I've got to show that if I have two elements in C of A, I multiply them together, I stay in C of A. So how do I show that xy is in C of A? Well, C of A is all the elements that commute with A, so I've got to show that xy commutes with A. So I'm going to start with xy on the left of A, and I want to get xy on the right of A? Well, I'll just do it one step at a time. I'm going to be using associativity in my group, so the first thing I'm going to do is move the brackets over and put them around YA. So that's by associativity. So I'm not writing down the right-hand reasons here, but I am saying them. That's by associativity of the binary operation in G. I can always move brackets around. And this is very much a follow your nose proof, in that each line there's nowhere else to go but the kind of obvious thing. I'm now going to use the fact that y is in C of A, so I can swap y and A around. So that's using the fact that y is in C of A. So YA equals AY. And now I'm going to get x and a next to each other by using associativity again. So that's using associativity again. And now I'm going to use the fact that x is in C of A. So as I said, this is very much following your nose. And then I'm almost finished. I've got to get x and y grouped together by using associativity once again. So that's using associativity again. So now I've got what I want. Just summarise my few lines of computation. XYA is the same as AXY. So I've got x and y from the left of A onto the right of A, so in other words xy commutes with A, so we conclude that xy is in C of A. So I've just moved the previous bit of paper so that equal sign is kind of hovering in the middle of nowhere at the moment. So we've got closure. Okay, if we've got two elements in C of A, we multiply them together, we stay in C of A. Is that okay, everyone? Okay. What about the identity element? I want to check that the identity element lives in C of A. So as usual, we'll call our generic identity element little e. So we're going to show that E is actually in C of A. So I've got to show that the identity element commutes with A, which is just part of its being an identity element. And I'm going to use both the fact that it's left identity and the right identity. This is very easy. So that's just because E is the identity element. So EA is A because E is an identity on the left, and A is equal to A because E is an identity on the right. It's a two-sided identity element. So that's just purely property of identity element. So notice we're using the various properties of G being a group. We've used associativity, we've used the fact that it's got an identity element, and the properties of the identity element. So E is in C of A, which is good. Then finally, the third thing we have to prove is that inverses are present. In other words, if you've got an element X in C of A, then its inverse is also in C of A. Okay, so X's twin or partner, whatever you want to call it, is also lurking somewhere in C of A. So let's consider X inverse. So that's certainly an element of the group G because it's a group, so we've got inverses. What I want to do is show that X inverse is in C of A. So as we've gone through this semester, we've developed our proof writing techniques, and as I've said several times, there's nothing wrong with occasionally saying what you're going to do next. It helps you to structure your proof, it helps you when you read through it again, it helps whoever else might be reading through it. So occasionally just say what you're going to do next, and then perhaps when you've done it, say that you've done it. There's nothing wrong with putting the odd English sentence in just to help the flow. So we're going to show that X inverse is in C of A. Perhaps I should have just said, as I did in the part 1, to expand this, saying that X is in C of A means that XA equals AX. In other words, X commutes with A. And now I want to show that X inverse commutes with A. So what can I do? Well, one way to do it is just to start with XA equals AX, and then just rearrange this by multiplying it by X inverse on the left and on the right. So let's do it one step at a time. So I'm going to pre-multiply or multiply on the left by X inverse. And we'll do this quite quickly because there's nothing unsurprising happens. Again, we use associativity. And some of you may want to do this computation a bit more quickly and miss some lines out. So we get X inverse X, which is the identity element. So we get down to A is X inverse AX, and then so there I've used properties of the identity element, and now I post multiply by X inverse, and I'm really putting every single line in here, which, as I say, some of you may want to skip. And I probably will miss one or two lines out now. I've got X inverse there, which is the identity. So I've missed a line or two out there. Using associativity. So I end up with AX inverse equals X inverse A. There's a lot of lines there, but they're all kind of trivial use of group properties. Well, trivial now, of course. 2 months ago you would have wanted to put even more lines in, perhaps. So what we conclude is, well, I'll write that the other way around because I was putting the X's first before the A on the left. Okay, so we've ended up with X inverse commuting with A, which is what I wanted. So we conclude that X inverse is in C of A. So starting from XA equals AX, I could use that X inverse A equals AX inverse. Okay? So what we've got then is that C of A is a subgroup of G, because I've checked all three parts of the subgroup criterion. Is that okay? Okay, so what we've got actually then is a subgroup of G. So it contains the identity. So this is our kind of typical picture with a G, the big group, and then a subgroup, a little oblong at the end. So it contains the identity, of course. Can we say anything else about C of A in general? Well, it actually contains the subgroup generated by A. So remember, the subgroup generated by A is a set of all powers of A, and any power of A will commute with A. So let's just prove that. So let X be in the subgroup generated by A. So that means that X is some power of A, because that's what the subgroup generated by A is. So the power could be positive, 0 or negative. And any power of A will commute with A. So let's just write that down. So then XA is A to the K A, which is A to the K plus 1 by index laws. Remember, A is A to the power 1. And then we just write that the other way around. Okay, so I'm just using index laws there to show that any power of A commutes with A. So any element of the subgroup generated by A is in C of A. So I haven't put the right-hand reasons down there, but I'm using index laws, and I'm using the fact that K plus 1 is the same as 1 plus K, which is just commutativity of addition in the integers that you've been using for 15 years or more. And then we get XA equals AX. Okay, so that means that X is in C of A. Oops. So I started with something in points A. I've deduced that it's also in C of A. So that means that pointed brackets A, the subgroup generated by A, is a subset of C of A. In fact, it's actually a subgroup. I mean, that follows from a general remark that if you've got a subgroup of a group and another subgroup sits inside the subgroup, then the smaller thing will actually be a subgroup of the bigger subgroup. I haven't said that very well, but this is not just a subset, it's actually a subgroup. So going back to this picture, sitting inside C of A is pointed brackets A. And these are all subgroups of each other in the obvious way. So when you're computing C of A, you certainly know that you've got pointed brackets A in there. In fact, sometimes pointed brackets A is the whole of C of A, and sometimes it isn't. And we'll do some examples in a second. Okay, so we've got the big group G. We've picked an element A, and we look at all elements that commute with A, and in particular inside C of A, which is a set of all elements that commute with A, you will have pointed brackets A. Okay? So we've got C of A, which is a subgroup of G, and then we've got that chain. And some of these less than or equals, which means subgroup, could actually be equals depending on what A is and what G is. In fact, another remark, if you have an abelian group, then everything commutes with everything. So C of A for any element A will be the whole thing. Okay? And in fact, that's an if and only if. So G is abelian if and only if for every element in the group, C of A is the whole thing. So one direction of this implication is, this double implication is by definition of abelian. If G is abelian, then everything commutes with everything. So if you take an A, the set of elements that commute with A is the whole thing. Okay? So that is going from left to right. Conversely, if it's the case that for any element in G, its centralizer is the whole of G, then it's easy to see that G must be abelian. Because if you take two elements, X and Y, then the centralizer of one is the whole thing, which means that Y must be in there, so it commutes with X. You need to write that out, it's a few lines, but so what we're saying here really is that for abelian groups, centralizers are not very exciting. Because for abelian groups, every centralizer is the whole of G, which isn't very exciting. So it's only really for non-abelian groups that centralizers are interesting. Okay? So only for non-abelian groups are centralizers of interest. Because otherwise, for abelian groups, centralizers are always the whole thing. So our examples will be for non-abelian groups. So we should do a little example. And there's an example on your coursework as well for you to do. Well, let's take our smallest abelian group. Our smallest abelian group is S3, which we can think of as the symmetric group on three objects, or we can think of it as the symmetries of an equilateral triangle. We've looked at it in both ways. I'll look at it here using cycle notation, so I'm thinking of this as a symmetric group on three objects. So it's got 3 factorial equals 6 elements, and we've written down these several times using cycle notation. So those are the 6 elements. We've been playing around with cycle notation for 2 or 3 weeks, so now hopefully you're quite fluent in cycle notation. So we're going to pick one of these elements and compute its centralizer. Perhaps I should have made another remark when I was making my general remarks on the previous page. If I take the element A to be the identity element, which I could do, it's a perfectly good element in the group, then the centralizer of the identity is what? That's the set of elements that commute with the identity. What's that? Well, everything commutes with the identity, doesn't it? So the centralizer of the identity is always the whole group. Okay, so again, that's not too exciting. I mean, it's just the remark that the centralizer of the identity is the whole group for any group G. So we're not going to pick the identity to compute the centralizer. of, because that's not too exciting. So let's pick one of the other 5 elements, say this 3 cycle 1, 2, 3. So we're going to calculate the centralizer of the element 1, 2, 3. Well, going back to our remark on the previous sheet, we get some elements for free, which are the elements in the subgroup generated by the given element. So we might as well write down those first, right? So remember, going back to our oblong picture, we get these for free. We don't need to do any calculation beyond calculating the subgroup generated by the element. There may be some other things, but we certainly get those for free. So let's write down those first. So we know the subgroup generated by 1, 2, 3 is in the centralizer. So let's compute that first. Well, we know this. This is a 3 cycle. So it's got order 3. So there are 3 elements in this subgroup generated by 1, 2, 3 is the identity, iota. There's 1, 2, 3 itself, and there's 1, 2, 3 squared, which is the same as 1, 2, 3 inverse, which is 1, 3, 2. So we've done that calculation before. Okay, so I'll just say this again. 1, 2, 3 is a 3 cycle. It's got order 3, so there are 3 elements in this pointed brackets of 1, 2, 3. There are only 3 distinct powers. There's the identity, which is 1, 2, 3 to the power 0. There's 1, 2, 3 itself, which is 1, 2, 3 to the power 1. And there's 1, 2, 3 all squared, or if equivalently 1, 2, 3 inverse, which is 1, 3, 2. So if you're not sure about that, then perhaps afterwards you can just check that these are the 3 distinct powers. Any other power of 1, 2, 3 will be equal to one of these 3 things. So that just follows from our general theory of cyclic subgroups. Okay, so certainly the centralizer contains these 3 elements. Does it contain anything else? Well, unless